All right, welcome to this session. I first of all want to look at two chemical reactions. The first reaction is called the Clammensen reaction, and the second reaction is called the Wolff-Kishnar reactions. What really happens in these chemical reactions? What kind of reagents do we have when we're looking at the Clammensen reaction and the Wolff-Kishnar reactions? So first of all, I want us to understand to say the basic essence of these two chemical reactions or these reaction mechanisms is to reduce the ketones into the alkanes. So first of all, I mentioned to say we are having the ketones, okay? And then we want to reduce these ketones into what we're calling the alkanes. That's the main instance of these two reactions, the Clamisen reaction and the Wolff-Kishner reactions. I'm not so sure how you are going to pronounce the first name, the first reaction, but I'm pronouncing it as Clamisen reaction, and then the second one I'm pronouncing it as Wolff-Kishner reactions. So I want to dive into the reaction mechanisms. How do you work them out? And what are you supposed to consider? And what kind of reagents do you have when you're looking at the Clamisen reaction and the Wolff-Kishner reaction? So let me first of all give an example here. Since we're talking about a ketone, we are saying that when we have an example like this, okay? So we are having a ketone, and the structure of a ketone is this. I'm going to give this example. We have a ketone which is like this. Good. There we go. We have a ketone. So to reduce this ketone into an alkane, we need certain reagents that are going to facilitate this chemical reaction. So we are having the ketone here, and we need certain reagents that are supposed to be here for them to make sure that we have our end product as an alkane. So for a Clamisen reaction, and I will repeat that. For a Clamisen reaction, we have two reagents. The first reagent is zinc with mercury in the presence of an acid or in acidic conditions. This kind of an acid can be any strong acid. We're talking about HCl. We're also talking about the sulfuric acid. The HCl I'm talking about here is the hydrochloric acid and also the sulfuric acid. So when you're trying to convert, or when you're trying to make sure that you have a reaction mechanism that is talking about converting the ketones into the alkanes, we mean when you have zinc with mercury in the presence of an acid which is the HCl or any strong acid such as sulfuric acid, we are saying this kind of a reaction is called a Clamisen reaction because you get to convert the ketone into the alkane and you're going to have your end product as this. So you're just going to break down this the double bond that is here, that is trying to emphasize the point to say this is the ketone because you know to say this is the whole structure of the cyclohexane, which is double bonded to the oxygen, and when it breaks you're going to have two atoms of what? The two atoms of hydrogen. So when you have this conversion, while you are having the breakdown or the conversion of a ketone to an alkane under the presence of the zinc and the mercury, again in the presence of an acid, we're talking about the Clamisen reaction. Okay, so this is how it proceeds. So anytime you have such kind of reagents, you come across such kind of equation where they're telling you to say you have a ketone has been given in this chemical reaction, and then they're trying to tell you to say predict the end product of this chemical reaction, and you're having your reagents as zinc with mercury, and also you have your acidic solution there, which is the HCl or the sulfuric acid. I want you to note that the first thing that should come to your mind is that you're having the Clamisen reactions because the zinc plus the mercury that is here is making up what we're calling the Clamisen reactions. So I want you first of all to note that the conversion of a ketone to an alkane is a reduction method or reduction reaction. So this is we're just simply reducing the ketones to what? To the alkenes. And this is how it simply works out. So the Wolff-Kishner reaction, equally the same thing. We are just trying to reduce the ketone into an alkane. Sorry, this is not an alkene. This is an alkane. There's no double bond there, so this is an alkane. So the main instance of the Wolff-Kishner reactions, as well as the Clammensen reaction, is to make sure that we reduce the ketones into the alkane. I want to make sure that I provide a reaction mechanism that is going to show how the Wolff-Kishner reaction takes place. But in the example of an Wolff-Kishner reaction or a Wolff-Kishner reaction, this is how it works out. So you have what I'm calling the Wolff-Kishner reaction. Okay. So under the Wolff-Kishner reaction, the reagents differ from the Clammensen reaction. What do we have here? So when you have such a thing, we're saying this is called a ketone as our reactant, and I'm trying to make sure that I reduce this ketone, and I'm saying this is a reduction method. I'm reducing this ketone to an alkane. So this takes place in the presence of an hydrazine, which is H2N, to NH2, and then it takes place in the presence of a basic solution. So we are going to have a strong um, basic compound here that can be sodium hydroxide, that can be potassium hydroxide, or any strong base that can facilitate this reaction. So I first of all want you to note the difference between the Clammensen reaction and the Wolff-Kishner reaction. Under the Clammensen reaction, we were having the zinc plus the mercury in the presence of an acid to reduce the ketone to the alkane. That is what we are calling the Clammensen reaction. And then with the ketone, we are having the hydrazine in the presence of a basic solution to reduce it to an alkane. So a ketone is being reduced to an alkane in the presence of an hydrazine and in a basic solution. That is the Wolff-Kishner reactions. And then the Clammensen reaction, we're having the zinc and the mercury in the presence of an acidic solution, reducing the ketones into the alkane. That is what we're calling the Clammensen reaction. So please let us try to see how we can make a clear distinction between the Clammensen reaction and the Wolff-Kishner reaction. So this is how it proceeds, and here our end product is still going to be the same. What are we trying to achieve? We're trying to come up with an alkane. So I'm just going to add two atoms of what? The two atoms of hydrogen, and you know this is just cyclohexane. This is a ketone, but the end product here is cyclohexane. What am I trying to achieve? I'm trying to convert the ketone to an alkane. So in the next video, I'll be looking at detailed explanations on how you're supposed to come up with a reaction mechanism for the Wolff-Kishner reactions as well as the Clammensen reaction. But for now, when you get back to your tutorial sheet question 3, there's a point where we have to we have been given a question and we've been taught to predict the major products, and it was a Wolff-Kishner reaction. So you know now the role of the Wolff-Kishner reaction, the Clammensen reaction. We are trying to make sure that we reduce the ketone to the alkane. The zinc and the mercury in the presence of an acidic solution, that is the Clammensen reaction. The hydrazine in the presence of a strong basic solution, that is the Wolff-Kishner reaction. So that is the main difference between the two half reactions. So I just thought of emphasizing the difference between the Wolff-Kishner reaction as well as the Clammensen reaction. Thank you so much.